And hello, welcome to this video on turbulence modeling. We're going to continue the DDES discussion, delayed detached-eddy simulation. And in the last video, we're talking about some blending functions which help us to deal with the model stress depletion phenomena. Now, why was the model stress depletion phenomena important? Okay, so why is this important? Well, this actually means, okay, yeah, I already told you what model stress depletion was, but what I didn't quite clarify was that model stress depletion, okay, MSD is dependent, okay, degree of MSD is dependent on, okay, on how you structure your grid. Okay, so what does this mean? In other words, this means different grids in boundary layer give you different results. Okay, so this is the key problem with this model stress depletion. It is because it's grid dependent, and depending how you structure your grid around the surface or what have you, you will have different results, and that's very troubling. So you want to kind of get rid of this phenomena so that you won't have a model stress depletion that it's really based on your grid. So all these blending functions are to, okay, blending functions get rid of MSD, which model stress depletion, which stress depletion, which is based on grid structure in boundary layer. Okay, so it means that different grids in boundary layer should give more or less same results, which is definitely what you want. Alright, that's the intent of this delayed detached-eddy simulation, which means that you don't want your LES to kick in prematurely, and then you have this model stress depletion, and therefore you have different results. Okay, so what results are we talking about? Okay, the different result is, okay, the different result is this. It is that premature flow separation. So remember what flow separation is? Flow separation is where, you know, the attached part of the flow, the boundary layer, okay, a good chunk of it starts to you know, take off, so to speak. So remember the classical case of flow separation. If you have a flow around a sphere, for example, then you have this flow here, and this is your velocity profile, and somewhere down the line the velocity profile will, you know, will have this kind of opposite swirl. So you'll have this kind of swirling motion here. Okay, so this is the flow separation we're talking about, where this part of the velocity here starts to stall, it starts to slow down and then go into the opposite direction. Now, if this happens prematurely, okay, if this happens prematurely due to the grid, so it means that the grid will give you model stress depletion, okay, the incorrect grid, or in this case we have the paper called ambiguous grid. I explained that in the last video. Ambiguous. Why is it ambiguous? Because said before, the parallel distance, it kind of allows for LES to kick in within the boundary layer, which is not what you want. Okay, so you either want LES throughout your boundary layer or rents through your boundary layer. If you have rents and LES in your boundary layer, then you kind of have a problem there. with a model stress depletion, and this will cause premature separation. Premature separation. So what does it mean? Depending on your grid, the place at which this separation phenomena starts, it can differ, and then that's very troubling, at least for the aerospace application. So you don't want to have the grid causing this premature separation. So this whole process is called grid, in this paper it's called grid induced separation. And the whole point of this DDES is to prevent this with the use of blending functions. Okay. So yeah. So blending functions prevent onset of LES within boundary layer when it's unwanted. So we won't have this grid-induced separation occurring. So what are these blending functions like? We have a tangent function here. Okay, we have a tangent function here. And in this tangent function, there's another function called RD, which is based on the turbulent viscosity. Turbulence viscosity and the gradient of velocity. Okay, so this is the gradient of velocity. You take the magnitude of that, and of course the von Karman coefficient and d. All right, so you will have a d, this turbulent length, or this d scale, the length scale of your DES. It is based on, of course, the distance from the wall, but it's also based on FD, which is this blending function, and it's ultimately also dependent on the turbulent viscosity and the local velocity gradients. So this kind of makes D a little bit more sensitive, not just to the grid itself, but also the velocity vectors, the velocity gradients, and the turbulent viscosity. Okay, so you can imagine if hey, hold on, wait a minute, I made a mistake here. This is a hyperbolic tangent, this is not tangent. Okay, so I just got to correct this. Okay, this is a hyperbolic tangent, not a tangent. Okay, so just want to make sure that's right. Pardon the typo. Okay, so let's investigate the behavior of this and try to make some sense of it. Okay, let's investigate the behavior of the blending function. I'm not going to do it as detailed as maybe the SST model I did, but just give you the rough behavior. Let's investigate the behavior of the blending function. Okay, so first thing first, hyperbolic tangent. All right, hyperbolic tangent graphs. Okay, in the positive regime, okay, x more than 0, right, they will have this kind of behavior where you kind of get a asymptote 2 between 0 and 1. Alright, so asymptote between 0 and 1, this is a y and x. Alright, this is y equals to, it's not an asymptote per se. This is a, yeah, this is actually hitting 1. This is not an asymptote. Pardon me. Yes, tangent, hyperbolic tangent of x. Now, of course, if you were to do a reverse, you want to do a 1 minus hyperbolic tangent of x, then you have something like this. Okay, so like this. Okay, 1 minus hyperbolic tangent of x. So you see, it is okay in low values of this, low values of x, it will be 1. Okay, low x, it means that this become 1. So I'll just number it like so, y2 will go to 1. Alright. So that means we can say at low RD, okay, FD tends to 1. Okay, when FD tends to 1, FD tends to 1, alright, FD tends to 1, then what do we have? Alright, so FD tends to 1, we will have this behavior. FD tends to 1, then we'll just have this. And what is the max of 0 and d minus c DES delta? Alright, what this max function is just to prevent this function from going below 0. Okay. Alright, so it will be this, it will take this value except when this is negative. Alright, when, okay, that means if d minus c DES delta less than 0, okay, d tilde equals to d, otherwise if it's the other way around, if it's more than 0, then you would have this value, this take the value. Alright. If it's more than 0, you will just get CDES delta. And what does this mean? This is Rand's mode, and this is LES mode. So what do we have when FD equals 1? We have classic DES behavior. Alright, so how about when the converse, DES equals to 0 or DES goes to 0? Alright, or D tilde, or FD rather, FD goes to 0, we get D tilde just equals to D. Right? You have this part equals to 0, this whole term disappears, then we'll have this. Alright, so this is also Rand's mode. Rand's mode. Okay. So yeah, what triggers FD to be more towards 0? Okay, what triggers FD to go to 0? FD goes to 0 when you have large, RD, large RD. So large RD triggers FD goes to 0, So that means that large RD triggers Rand's mode. So this is an additional way you can trigger the Reynolds average Navier-Stokes mode, okay, of the DDES. So this is what so special about DDES. Okay, so let's take a look at this FD. Okay, otherwise you have a blend between the Rand's mode and the classic DES mode. All right. So yeah, this is a blending function to kind of delay. I mean that it gives you one additional path. You can think of it. It gives you one additional path to getting this what do you call that? Rand's mode. So it should give you, in the case of ambiguous grids, where you have LES kick in too early, it should give you Rand's behavior. So it takes out the LES and gives you Rand's here, giving this additional extra path that you can start to trigger Rand's. Alright, you can start to trigger Rand's mode. Alright, so what's large RD means? Okay, we have large RD here. Large RD means okay, it means that you have large turbulent viscosity in comparison to this. That's one way of looking at it. And now what does this mean? Okay, large turbulent viscosity means large RD. Okay, large RD. Okay, and in other words, large turbulent viscosity triggers. So large turbulent viscosity triggers Rand's mode. Okay, or rather prevents LES from switching on. Okay, so how does, yeah, so this is large turbulent viscosity. So effect of large turbulent viscosity is this. It's called, yeah, effect of large turbulent viscosity is this. Okay, so what are the other things that can affect, that will change? The D will, D makes RD small. Okay, so that's quite consistent because yeah, that's quite consistent because in LES mode we want okay, yeah, in LES mode we want RD to be small so that FD will go towards 1. Okay, so if FD goes to 0 we get Rand's, FD goes to 1 we get the DES or LES modes. So D makes R, okay, large D makes RD small. That means away from the wall you have LES. That completely makes sense. Then you have this little gradient as well. Okay, large gradient makes RD small. Okay, so RD small means you, okay, large quantity of gradient, you get RD to be small. Okay, so large this velocity gradient or large magnitude of velocity gradient makes RD small. Why is this good? Because when you have a large velocity gradient, okay, large velocity gradient, it naturally generates eddies, right? Naturally generates eddies or flow instabilities. So this makes it okay for DES or LES to kick in. Okay, so yeah, this one helps us to switch from Rand's to DES because when you have a large shear or strain rate, okay, large strain rate or large shear rate or even a large velocity gradient for that matter, it causes you know, flow instabilities. Then you can let LES kick in without the modeled stress depletion, because now you can generate enough eddies to make up for your loss in turbulent viscosity. Okay, so these two kind of make sense for RD. And the other thing is the turbulent viscosity. Alright, large turbulent viscosity triggers Rand's mode, or rather prevents LES from switching on. So this is good because well, okay, this is good because normally in your buffer layer, or rather your boundary layer, you have your Rens model. Okay, your Rens model, and nu t is modeled here. Nu t is high, and in your LES, okay, nu t is low. Okay, but in your shear region, this is okay. Your only concern is this maybe the top 1/3, top 33% of your boundary layer. If your LES switches on here, you'll have model stress depletion. Now, if okay, over here you have your Rens. Okay, you have your Rens region. Okay, you have your Rens region, and you have a very steep velocity gradient there, and you have a high nu t here, for example, in your Rens region. Okay, and then this is the Rens boundary layer, the LES boundary layer. So this is the faulty version, right? So you have a high nu t here. What does that do? Okay, when high nu t here, it means that your RD will also be high. Okay, so in this zone, nu t high means RD high. If your RD is high, that means it will try to make FD go towards the Rens region. Okay, RD high. Remember, RD high means FD goes to 0, means we get Rens behavior. So FD goes to 1, we try to keep it Rens. That's what this thing is for. So instead of, okay, over here your viscosity is high, over here your turbulence viscosity is low, over here your turbulence viscosity is low, and then you have this sudden drop, right? So normally if you have this model stress depletion problem, you have a sudden drop. Okay, and that's how I like to think about it. You have a sudden drop in nu t. Okay, so probably it starts at 0 near the wall, it goes up, and then suddenly, let's say this is your LES boundary layer, this is your Rens boundary layer, there's a LES boundary layer. Okay, suddenly there's a drop, which is kind of artificial because you switch to LES a bit early, so the makeup for turbulence isn't there. So yeah, you have a sudden steep drop here. I don't really know what this shape of the curve is, but model stress depletion means there's a sudden drop in nu t. So it drops nu t without compensating with actual flow instabilities, right? Oopsie, phone call there. Anyway, so without flow instabilities, all right. Okay, so I mean the shear rate ensures we have enough flow instability before we switch over to LES. That's why you have this in there. But what this does, this delay function, it means if, let's say, you have a high degree of turbulence viscosity, it will say, okay, wait, my high turbulence viscosity, okay, high nu t means RD is high. RD is high locally, okay, in the cell. And let's say this box here, the cell. So if this is distance, for example, right? It means the RD is high locally. That means I want to remain in Rens mode. Okay, so I say to this cell, hey, I want this to remain in Rens mode. Okay, so I want to delay the onset of DES or LES. So it maintains with a high turbulence viscosity. It maintains a Rens mode, which or it slows down the descent into LES or DES. Okay, so what happens is in the next cell, since you have a high turbulence viscosity here, it can be transported or diffused. It can diffuse into the adjacent cell, and it makes the cell next to it also have higher nu-T. And this will also trigger the local RD to be such that you want Rand's mode to stay. Okay, so what it means is that high nu-T will try to stop the sudden descent, so to speak, into DES or LES mode. Instead, it makes the descent a little slower into the LES mode, so that only beyond the boundary layer, then you can have this very low nu-T value that fits the subgrid viscosity. So over here is the hybrid between your LES and Rand's mode, or DES and Rand's mode, and so it makes this drop in turbulence viscosity a lot more gradual. And by doing so, you allow, as you go towards the free shear regions, you have more and more flow instabilities. You have more like flow gradients, like especially over here. Here you have especially in the outer boundary layers, you have high amounts of shear, strain rate, so that you can generate your turbulence. So that makes it a more appropriate place to let go that nu-T and let DES kick in. So the long story short is that when you have high nu-T, it makes it kind of delays the onset of turbulent LES. Delays the onset of LES or DES. So that's why it's called delayed Detached-eddy simulation, and this actually helps prevent the model stress depletion. Okay, it means that your the amount of turbulence you simulate, when you combine the turbulent viscosity with the natural flow instabilities which you resolve, that will be enough, and that should model the flow correctly, and it should prevent LES from kicking in prematurely in the boundary layer. So that's what this blending function does. So just to give you some sort of intuitive feel to this RD, hopefully that helps with the interpretation of what all these things are doing. So it just basically helps to prevent the onset of LES based especially on this nu-T. Alright, so these two, I explained to you what they do and why you probably want them there, and these are ways to give you intuitive feels into the DES model. So yeah, I know I kind of run a little over time. I don't really like my videos to be more than 20 minutes, but okay, hopefully that settles the understanding for DES mode. So DDES, sorry, delayed detached-eddy simulation. Okay, so thanks for watching. I'll see you guys next time. Bye bye.